Welcome to calculus. Whether you've taken pre-calculus 12 already in the past or are taking this concurrently with AP Calculus AB, this video will prove to be extremely beneficial for you because you need to know the foundations of what makes calculus what it is before you can really understand it. So in these next couple of videos that I'm going to show you, please understand that you need to pay attention to these and that you need to have an extremely high level of understanding and mastery of this material here before you actually take calculus. So we're going to focus on functions and transformations for this video. And as a review, we're going to learn about what a function is. We're going to learn about how to graph and find domain and range, and a couple of other things. So to start, we're going to be looking at what a function is. More importantly, what a one-to-one function is, what a function actually is if it's not one-to-one, and at the end, what is not a function. So by definition, a function states that any input that has one output is a function. So I'm going to use the stuff on the right here. If I plug in 1 and I get 2, if I plug in 3 and I get 4, if I plug in 5 and I get 6, and if I plug in 7 and I get 8. We call the left side the x and the right side the y, and if you really want to be technical about it, this is the input and this is the output. You'll notice that the input of 1 only relates to the output of 2. The input of 3 only relates to the output of 4, same thing as 5 and 6, and 7 and 8 respectively. So if I were to plot these out over here, 1, 2, 3, 4, and 1, 2, 3, 4, 5. 1, 2, 3, 4, and 5, 6. There you are. And if you would like to connect them, that's okay as well. There you are. Okay. So that is the definition of a one-to-one function, where every input has a unique, and by unique I mean individualized, output. Now let's go look at what just a function is. So if I have 1, I can point to 1, 2, I can point to 1, 3, I can point to 1. And so my inputs and my outputs still follow the defining, the defining property of a function, where every input only relates to one output. If I plug in 1 to my x's, I get 1 for my y's. If I plug in 2 to my x, I get 1 for my y. And if I plug in 3 to my x, I get 1 for my y. Every input only has one output. But if you look at this output, it has multiple inputs, which is completely fine. Okay? I can have as many arrows pointing towards the y's, but for every individual x value, I can only have one arrow leading out of it. So once I start to plug things in, 1, 1, 2, 1, 3, 1, here we go. And then you can draw a line over here. So that's what we call a function if every input only has one output. It can be the same output as all the other inputs, but we just want one arrow leaving out of every designated x value. And so let's look at the non-functions. If we plug in 1 into our x, and then 1, 2, 3 for our y's, and the input leads to multiple y values, we call this a non-function. And in grade 10, you learn why the reasons for it not being a function is and how it doesn't make sense in real-world applications. So 1, 1 is here, 1, 2 is here, 1, 3 is here, and we see that we have a vertical line. So before we get into the bottom part of continuous and discontinuous functions, I wanted to go over another way just to double check and see how you can quickly tell if a function or if an equation is a function or not. First thing we're going to do is we will do what we call a vertical line test. So let's say I have a function from here to here, or a graph from here to here. I'll have this vertical line over here, and what I'm going to do is make sure it's completely vertical. I'm going to swing this all the way across from left to right, or right to left. If at any point it makes contact once and only once, then we call that a function. So if I swing this around, it only hits the graph once at any designated point I choose. And that's a function. Okay. So if we pass this vertical line test, then we know that it's a function. So if we have another graph that looks kind of like this, let's say we have a circle, okay, and we bring in our vertical line, this is not a function. Because if you look, this part, it hits twice. And by definition, if we use a vertical line test, if we swing it across from left to right, it has to only hit once at the most. If it hits more than once, then we deem it as not a function. All right, so if it fails, it's not a function. Now, going over here for the vertical line test, we know it's a function. How do we test if it's a one-to-one function? So if you pass the vertical line test, you can use the horizontal line test. And that deems it to be a one-to-one function or not. So let's look at the straight line we had earlier. Maybe the points are a little bit different. That's okay. If we take our vertical line like this, and we swing it from left to right, it only hits once. So we know it has to be a function. Now, the same idea with the horizontal line test. We have a straight line, but we swing it from up to down or down to up, or bottom to top. At any point, if the most it makes contact with the line is just one instance, then we have proved it to be a one-to-one function. And that's clearly the case over here. It only hits once. Good. So that's what we call a one-to-one function. Now, let's look at something like this. Okay, some sort of graph that looks really weird. If we take the vertical line test, we obviously pass. It only hits the black graph at most once if I swing it from left to right. So it passes the vertical line test, but if we do the horizontal line test, it fails in a couple instances. Okay, over here, it hits twice, which is no good. So that's the basic understanding of what a function is and isn't. Now, let's go to the idea of a continuous and a discontinuous function. A continuous function means from one end to the other, there are no stoppages or holes. So if I have one point from here and another point from here, it doesn't matter how ugly I make my function to be. It can be like this. If there are no holes, then we call this a continuous function. And so I'll explain what I mean by a hole. So let's say we want to get from this point to this point. And I go from here to here. And then I skip a little bit and I go from here to here. And I skip a little bit and I go from here to here. The parts I'm highlighting right now are the little gaps, the spaces in between one end to the other. So this is what we call a discontinuous function. It's discontinuous because there's some sort of stoppage, either towards the beginning or the end or in the middle. There's something that doesn't make it a perfectly smooth line. Now, let's go ahead and look at what a continuous function domain and range looks like. So let's say I have a line over here, boom, boom, and we've learned this in the 10th grade before, but I'll go through it again. Domain refers to the x-axis points, the leftmost and rightmost x-axis points. So if I look at the domain, it'll tell me, oh, what is my leftmost x value? Oh, it's right here, which is -4. 1, 2, 3, 4. So -4. And what is my rightmost? Oh, 1, 2, 3, 4. So it's 4. And we denote it like this, -4 to 4. We put square brackets, and I'll explain what the square brackets means in just a bit. Okay. These endpoints are what dictates whether this is a square bracket or a round bracket. If you look at the endpoints, we know it includes the -4 because it actually touches it. So my square brackets are what we call inclusion brackets. Now, let's say I had something a little bit different over here, and I had a hole in both of these. There. What this tells us is I can get as close as I possibly can to -4, but I will never hit -4. I can get really close, so -3.9999999 is a point there, but I can't actually hit -4. So if that's the case, I put a round bracket. And these are what we call exclusion brackets. Because they get very, very close to our designated endpoint, but it doesn't actually hit the endpoint. We would close off the 4 with a round bracket as well, because you see it's getting very, very close to 4, but it doesn't quite hit 4. So that's how we do domain. Range is still extremely similar. So for this particular question, what is the lowest it can be? Well, judging from the fact that we looked over here, the lowest it can be is -1. And it has to be an exclusion bracket because it doesn't actually hit -1. And if we go to our very highest, we see that, oh, it gets really close to 5, but it doesn't quite hit 5. Another way to write these, and I'm going to erase the stuff on the right just because you guys can just go back, review, copy down notes, doesn't matter. But another way to write this is to say we go from -4 to 4, and then it's an inclusion and an inclusion on the left and right. So we put less than or equal to x and less than or equal to 4. That's our range. But if we look at our domain, that's our domain. But if we look at our range, very similar. Sorry, I apologize. It doesn't actually hit the 4, so it's less than 4. And yeah, -4 is less than x, which is less than 4, because it doesn't actually hit the 4. So that's our domain. If we look at our range from -1 to 5, once again, it doesn't actually hit -1 or 5, so -1 is less than y, which is less than 5. To properly review, we're going to go through a couple more examples. Let's do 2 more. Let's say I have something like this, and I travel all the way here, 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 and there. From, if we want to look at our domain, then from -4 all the way to 1, 2, 3, 4, 5, 6 to 6, that's where my function is. On the left, I have an exclusion bracket, And on my right, I have an inclusion bracket because it doesn't hit -4, however, it does hit 6. You can write it like this, or you can write it -4 is less than x, but less than or equal to +6, because once again, it does not hit -4, and it does hit +6. If we look at our range, the lowest it can be is -2. And the highest it can be is 1, 2, 3, 4, 5. For the lowest, it actually hits -2, and for the highest, it gets very close to 5, but it doesn't hit 5. And if we wanted to write our domain and range, it's -2 less than or equal to y, which is less than +5. All right, for the very basics of a discontinuous function, these are fairly easy. If we look at all these points over here, these are all discontinuous points because there's a bunch of different holes. If I were to draw this out over here, if you notice, there's a hole in between this, here, 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 here. So we wouldn't have the less than or equal to or greater than or equal to, stuff like that. We would just say, our domain, what are all the possible values of x? From left to right, x is the element of the set of numbers of -4, -3, -2, -1, 0, and 1. And for our range, y from lowest to highest is the element of the following set of numbers: 0, 1, 2, 3, 4, 5. Because that's what the y values are for all these over here. You will see other functions, namely some that look like this. Okay. And the domain and range are going to be just a little bit harder there to figure out, but we'll save that for calculus. So let's go ahead and move on to the next part. Combinations of functions. Use the functions f of x and g of x below to compute the following combinations of functions there. So let's say we're given that f of x is equal to 3x plus 2, and g of x is equal to x squared minus 4. Sometimes when we combine functions, it's easier, instead of writing f of x plus g of x, it might be easier to say, I want to do f plus g, where my variable or my input for both of them is x. And to be fairly honest, I do prefer this one here because there's less room for ambiguity. But you'll see this in a lot of textbooks, and they're perfectly valid. You do need to know both of these properly. Once again, I do prefer to write f of x plus g of x, okay. But it's only a matter of preference, and both are acceptable. What you do now is, what is f of x? Well, that's 3x plus 2. And what's g of x? That's x squared minus 4. And although I don't necessarily need the brackets, I like to get into the habit of putting brackets around all of my functions, because when we get to multiplication and division, even subtraction at times, it makes things a lot easier. So 3x plus 2 plus x squared minus 4, because we realize there's no multiplication going on, there's no negatives on the outsides of the brackets, we don't really need them. So this is the same thing as 3x plus 2 plus x squared minus 4. And in the 10th grade, we've learned how to order things properly. This is x squared plus 3x minus 2. And that is my answer. We can keep going. F minus g of x is the same thing as f of x minus g of x, which is 3x plus 2 minus x squared minus 4. And this is where putting functions into brackets before we start combining them becomes really important. If we look at the first one, you can care less, you don't need the brackets. But if you look at the second one, you definitely do, because the negative bombs in, boom, boom, and becomes negative x squared and positive 4. This is now negative x squared plus 3x plus 6. That is your answer here. Fg of x is the same thing as saying f of x multiplied by g of x. You might even see it look something like this. F times g of x. I do prefer when things are split up like this, but once again, it's up to your discretion what you would like to use. All you need to know is that we need to plug in actual things into f of x and g of x. So f of x is 3x plus 2 from earlier. And what we're doing is we're multiplying by g of x. Oops. Which is x squared minus 4. We can use FOIL, we can use the distributive property. But this is just 3x cubed minus 12x plus 2x squared, what is this, minus 8. And if you want to organize them, which I highly suggest you do, you just get 3x cubed plus 2x squared minus 12x minus 8. And last but not least, we have f over g of x, which is f of x divided by g of x. This is just, let's use this over here, 3x plus 2 all the way over x squared minus 4. At this point, really no point in dividing things. If you've taken pre-calculus 12 already, you'll know what to do. But for now, we can just leave it like this. All right, but what's the point of having all that if we don't use real numbers? So let's say I want to redo these, but I want to use actual numbers here. So let's say I want f plus g of 2. So that's the same thing as saying f of 2 plus g of 2. In order to find out what f of 2 is, take the 2, plug it in here. So f of 2 is equal to 3 times 2 plus 2, which is equal to 6 plus 2, which is 8. So f of 2 is equal to 8. We do the same thing with g of x. Okay, g of 2, g of 2 is equal to 0. So this becomes this, which becomes 8 plus 0, which is just 8. You could do the same thing for f minus g of 2. So f minus g of 2 is the same thing as f of 2 minus g of 2, which is 8 minus 0, which is still 8. Okay, this is a very boring example. Okay. I'm not going to go over multiplication and division because you should know how to do that already. And now I'm going to go through function combinations using these. Okay. So how you would do things over here is you would say, okay, look at the actual points where the x and the y values give you a really nice, nice value. 1, 2, 3, 4 there, and maybe 5. And 1, 2, 3, 4, and 5 there. I try to highlight them as best as I can. So what is f plus g of x? Well, let's do this slowly. F of x and g of x. We can add for the x values when x is equal to -4, -3, 0, 2, and 3, because they all have a y value associated with every x value I just listed. I'm going to do this pretty fast, okay? And hopefully you'll be able to follow along. But if we have to add all the y values at every single point over here that I just had here, boom, oops, here's what it becomes. So f of -4 plus g of -4, well, f of -4 gives you a value of 4. G of -4 gives you a value of 2. There. So this new function, f plus g of x, is at -4, gives you a value of 6. So 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. There you are. Here's your new function. Then we look at our next point. Oh, -3. F of -3 and g of -3. F of -3 is 0. G of -3 is 4. So if you add them together, 0 plus 4, that's 4, which is right here, at the x is equal to -3 line. Your next one is over here. Whoops. F of 0 is equal to 4. G of 0 is equal to 0. If you add them together, you still get 4. Okay. Then you do the next one. Okay. So f of 2, g of 2, this is 4, and this is -1. So that's 3. F of 2, g of 2 is 3. No, I'll use red actually. And finally, f of 3 and g of 3. F of 3 is equal to 0. G of 3 is equal to -1. Add them together and you get -1. So at 3, here you go. Once you do that, just connect as much as you can. There, here, here, and there you go. So if you do f of x plus g of x, if you combine this and this together, and you're adding those two functions, here's what you get. Okay. And I guess you would put the arrow here because it keeps going nonstop, as it says in the question. All right, I'm going to do this fairly quickly now. F minus g of x. So we look at these two terms first. When x is equal to -4, if we do this minus this, that's 4 minus 2, which is 2. So at -4, my y value is 2 if I combine them. Over here, that's -3. So that's 0 minus -4. This has a y value of 0. This has a y value of -4. 0 minus -4 is 0 plus 4, which is right here. Next one. 4 minus 0, still 4. 4 minus -1 is 5. And finally, 0 minus -1 is just 1. So if you like, and I would do this too, just combine them nonchalantly like this. And please include the arrows. It just makes things a lot nicer. We do not care about all the stuff in the middle. We only want to use the really nice points. Now, there are exceptions to that rule, but for what we need for Calculus 12, it doesn't really matter. All right. So we can add, subtract, multiply, and divide. Once again, you should be able to know how to do these now using the same idea we've taught before. But let's go to lesson 2.3. Use the given functions f of x and g of x to determine the following functions. So we know that f of x is this and g of x is this. So what is g of 3? G of 3 means you take the 3 and you plug it into all the x values. So g of 3 is 5. What about f of g of x? Well, this should be 3. F of g of 3. Let me just erase this quickly. Okay. So how I would write this is f on the outside and g of 3 on the inside, like this. What we are doing is we're taking a function and plugging it inside of another function. So f of g of 3 means you take the g of 3 first, you plug it in, and then whatever the value is, that affects your f. Well, we have to first find out what g of 3 is. And you know what? We actually have. G of 3 is 5. So instead of writing f of g of 3, I can write this as f of 5. And we know how to find f of 5. Plug it in here, and you realize f of 5 is just equal to 25. If you look at f of 4, f of 4 is equal to 4 squared, which is 16. Now, if you look at g of f of 4, that's g of f of 4. We go to the inside first. F of 4 is 16. So erase this, or you know what, just write this. G of 16. And all you do is you take the 16 and you plug it into the corresponding x for your g function, which is which is 2 times 16 minus 1, which is just 31. So I'm going to do f of g of 2. This is f of g of 2. I forgot what g of 2 is, or what even the g of x function is. So take the 2, plug it in here. 2 times 2 is 4. 4 minus 1 is 3. So this is f of 3. F of 3, take the 3, plug it into all the x's. This is just 3 squared, which is 9. G of f of 2, very similar. This is g of f of 2. What is f of 2? Well, take 2 here, that's 4. So that's g of 4. And then take the 4, plug it in here. 4 times 2 is 8, minus 1 is 7. And that is a solution. The whole idea of a composite function is you solve for one function, and then you take that answer and plug it into another function.